Alright, this would be Matt and Mike on the shell method.
Ooh, yes.
Alright, you might be asking, what is the shell method? Well, you know what? The shell method is used to find the volume between curves rotated about an axis or line with respect to y.
The volume, eh?
Yes, the volume, yeah.
Ah, good.
Alright, well, as you can see here by this lovely diagram written on by Matt, we have a basic equation for the shell method.
Yes.
V is volume.
Ah,
All right.
that's what we're trying to find.
Yes, it equals 2 pi times the integral. Yes, that is an integral.
That's what I thought it was.
From A to B. And you might be like, hey, what's A to B?
Well,
we could go into depth on that, right?
Alright. Well, why don't you explain?
Alright, A to B is the interval of integration. That's from one point on the graph to another point on the graph. Yes.
Is that green squiggly over there?
Yep.
Ah.
It is, but you know what? We're going to get to that in a minute.
Okay.
Alright, well, you might be asking, what do I take the integral of?
Yes, I was curious.
The shell radius, you see.
Yes, I see that.
That is what you're taking the integral of, the shell radius. You might be like, what's the shell radius? Well, the shell radius will be the distance from a point on a curve to an axis or line. Sorry, that was a little choppy. I'm a poor reader, but you know what?
It's okay. You know what? You know what's up. You do what you need to do.
Could you tell us about the shell height?
Ah, yes. All right. So you see the next point in the graph, in the interval that we're looking for, is the shell height right here. And the shell height is the equation that shows the distance from the y-axis or line of rotation. So it's basically the height of our shell. If you couldn't understand that yet. And then we have that little dy over there.
You might be like, why? That's not a dx.
I was wondering myself. Could you explain?
Well, you see, the dy is meaning you're taking the integral with respect to y.
Ah.
Or the y-axis instead of with respect to the x-axis.
This is odd. I haven't done this before.
Yeah, well, you know what? You might be like, hey, I kind of need an example to understand what's going on here. Well, we have a lovely one from the book. Alright, here it is. Find the volume of the region bounded by y equals the square root of x, the x-axis, and the line x equals 4. And here's this lovely graph I was drawn up.
Color-coded. Color-coded,
of course.
Yes.
Well, you see, let's just go through the basic thing. We got that down here.
Alright, there's your basic equation.
Basic equation. The volume equals 2 pi, of course, times the integral from 0 to 2. Well, where do you get that? That's not even on the x-axis. No. It's the y-axis, because remember, respect to y, from 0 to 2, because that's the y. Because as the y changes on every little point on the graph, that would be the y.
Oh.
And if you know what, let's just take a side note from here. If you don't know what's going on, or you can't really image it in your mind, alright, imagine this right here. Alright, you see this? It looks like a box here, but when you rotate a box about the x-axis, it's going to turn into a cylinder.
Right.
And you might be like, well, where's radius come in? Well, this would be this little distance, y, would be the radius of the cylinder.
Ah. So then it would be just a bunch of little shells, then you say.
Yeah. Every little point has its own little shell built up on one another. And this solid thing, once it's rotated around the x-axis, it's going to look like a solid bullet.
We can't say bullet in school, so how about a rocket top?
Let's go with the rocket top. That sounds a little cool. Alright. Well, for the next part, seeing as we got the y, because the y is always changing on every little point, we plug that into the equation for the shell radius. Next is the shell height. Well, we have the graph, and this is the line of the equation with respect to y.
Yes, it is.
Well, the equation of a line. I made a blunder there. My apologies. Where it's x equals y squared. Well, you see up here, that's the shell height, 4 minus y squared. You might be a little confused as to what that is. Well, see, the line at x equals 4, that's the max distance it can be.
Right. So then if you just take 4 and subtract our equation, then you're always going to have our distance.
Yeah, we're always going to have the distance from the origin point. Say it was 3. Well, 3 is between this curve.
Right.
It's always going to be in between.
It's spectacular.
It's pretty fun once you know how to do it.
It is. It's a great thing.
And that'll be the shell height. And you plug that into your lovely little equation down here. Remember, respect to y, dy.
Always.
Never put dx or Mr. Winkler. You'll just...
It's over. You just lost your calc career.
Yeah.
It's done.
You'll have a bad day.
Mm-hmm.
It's like French frying when you should a pizza.
Great analogy.
Once you put all this into your fancy-dancy calculator, you should come out with 8 pi.
Ah, yes. It's great.
And remember, since we are rotating the object around a line with respect to x, our equations must have respect to y.
Which is why when that blue line up there, how it says x equals y squared, you might have been curious earlier about why it was not y equals the square root of x, like we said. But since it has to have respect to y, then we squared it both.
Yep.
Make it
solve for x.
Yeah.
And you know what?
There you go.
Just to make sure you all get it. You might be asking, what is that?
What could this turn out to be?
That, my friends, that is a cat. Yep. You might be like, why are they drawing a cat? Well, you know what? Because you're happy. This cat is the symbol of your happiness now that you can use the shell method.
Look at that smile on his face.
Look how happy that cat is.
He has pretty poor feet. And
yeah, but you know what? He's a fat, happy cat. You know why? Because he can do the shell method.
It's even colored in.
You know what? I think that's +5 extra credit right there. Don't you?
I feel the same.
All right. That's beautiful. Remember, Matt and Mike on the shell method.